Hi everyone, today I'll be going through questions 20 to 30 of the 2007 Intermediate Australian Maths Competition. Each of Andrew, Bill, Claire, Daniel and Eva are either always lies or is always truthful, and they know which each of them is. Andrew says that Bill is a liar, Bill says that Claire is a liar, Claire says that Daniel is a liar, and Daniel says that Eva is a liar. What is the largest possible number of liars amongst them? So they split it into cases. 1, Andrew is a liar, and 2, Andrew is truthful. In case 1, Bill is truthful, so Claire is a liar, Daniel is truthful, and Eva is a liar, so the total liars is 3. In case 2, Bill is a liar, so Claire is truthful, Daniel is a liar, and Eva is truthful, and the total liars is 2, so the maximum is 3. Question 21. On her birthday in 2007, Rachel's age is equal to twice the sum of the digits of which the year she was born in. How many possible years are there in which she could have been born? So first we analyze years in the form 19 something something. So the sum is 1 plus 9 plus a plus b, or 10 plus a plus b. The age is 2007 minus 1900 plus 10a plus b. We want the age to be twice the sum, so we substitute them in, factor out the 3, and we get this equation here, where we want to find 1-digit solutions for a and b. So there's 3 possible ones we can find. Now we analyze years in the form 2000 and something. So the sum is 2 plus 0 plus 0 plus x, or just 2 plus x. The age is going to be 2007 minus 2000 plus x. We look for ages 2 times sum, substitute them in, and the only solution this time is x equals 1. So these are the 4 years we found. So the answer is D, and I wrote some Python code that also finds these 4 only valid years, like so. Question 22. A border of black counters is placed around a rectangular array of white counters in a way similar to that shown in the diagram. If the number of white counters is equal to the number of black counters, how many ways can this be done? For how many different numbers of white counters, that is. So I let A equals the number of white counters, B equal the number of black counters, and L and W be the width and length of the rectangle, the inner white rectangle. So A equals length times width, B equals 2 times length plus 2 times width. When A equals B, length times width equals 2 times L plus 2W. Now we expand the brackets, collect black terms, factorize this, and we get L minus 2 times W minus 2 equals 8. So the possibilities are 2 times 4 or 1 times 8. With 2 times 4, the length and width are 4 or 6, so the number of white counters is 24. With 1 times 8, the length and width are 3 or 10, so the number of white counters is 30. And these are the 2 ways that it can be done. I also wrote some code here that finds 4 ways this can be done, but the 10 times 3 and 3 times 10 still have the same number of white counters, and the same for 6 times 4 and 4 times 6. So the answer is C. Question 23. We have a right-angled triangle with PR equals 3 and QR equals 4. Then we have a square inscribed in it, and we need to find the length of this side of the square. By similar triangles, QV on X equals 5 on 3, and X on RV equals X on 4 minus QV equals 5 on 4. Now we can substitute in QV equals 5x on 3. And we cross multiply and expand the 5. then we keep timesing both sides by 3, and then keep solving, and we get 60 on 37 is our answer, D. Question 24. There are 4 lifts in a building. Each makes 3 stops, which do not have to be on consecutive floors or include the ground floor. For any 2 floors, there is at least 1 lift which stops on both of them. What is the maximum number of floors that this building can have? So there are 12 lift stops altogether. Suppose there are 6 floors. By the pigeonhole principle, some floor has at most 2 lifts stopping there. Each lift connects this floor to 2 others, so that only 4 of the other 5 doors are connected to this floor. If there are 7 or more doors, some floor has at most 1 lift stopping there, and the situation is worse. Hence there are at most 5 floors, giving the answer B. This is possible if the first lift stops on floors 1, 4, 5, the second on 2, 4, 5, the third on 3, 4, 5, and the fourth on 1, 2, 3. Question 25. A bee can fly or walk in a straight line between any 2 corners on the inside of a cubic box of edge length 1. The bee managed to move so that it visited every corner of a box without passing through the same point twice in the arrow on the wall of the box. What is the largest possible length of such a path? So I've gone ahead and drawn the cube here. And since both sides, since you can't have 2 paths crossing at the same point, then there can only be 1 diagonal of root 3, because otherwise it would cross at the middle of the cube. And I've found an example path of the longest length, which has a length of root 3 plus 6 root 2. Question 26. What is the smallest number of odd numbers in the range 1 to 2006, such that no matter how these numbers are chosen, there will always be 2 which add to 2008? So pairs that add to 2008 are 3 plus 2005, 5 plus 2003, to 1003 plus 1005. Excluding 1, because we can't use 2007, it has to be in the range 1 to 2006. There are 1003 and then 4 division 2, so you just round down basically, giving 501 pairs. If we choose the number 1 and 1 from each pair, we get the maximum we can choose to not add to 2008 is 502. Thus the minimum to ensure 2008 is 503. Question 27. 2 semicircles of radius 1 are drawn on the diameter of a semicircle of radius 2. A circle C touches all 3 semicircles as shown. If the radius of the circle C is a on b, where a and b are integers with no common factors, then what is a plus b? So here we can just apply Pythagoras to the following right triangle, and we see that 1 squared plus 2 minus r squared equals 1 plus r squared. Then we can expand this out. The r's cancel, we solve for r, and we get r equals 2/3, which means a is 2, b is 3, and 2 plus 3 gives 5. Question 28. A lucky number is a positive integer which is 19 times the sum of its digits. How many different lucky numbers are there? This was quite tricky. Suppose the number has m digits and consider m greater than or equal to 4. Then the digit sum is at most 9m, while the number is at least 10 to the power of m minus 1. So 19 times 9m is greater than or equal to 10 to the power of m minus 1 for a lucky number to exist. But for m equals 4, 684 isn't greater than 1000. So it's worse for numbers larger than 4. So that means that our number must have less than 4 digits, any possible lucky number. Now we look at 10a plus b, so this is looking at two-digit numbers now, equals 19 times a plus b, has no solutions other than a equals b equals 0, so lucky numbers cannot be 2 digits either. So that means they must be 3 digits. Now consider 3-digit numbers in the form ABC. We have 19 times the sum of the digits equals 100a plus 10b plus c. Then 100 minus 19a equals 19 minus 10b plus 19 minus 1c. 81a equals 9b plus 18c. Divided all by 9, we get 9a equals b plus 2c. Now we try different values of a. So for a equals 1, we get b and c can be 1 and 4, 3 and 3, 5 and 2, 7, 1, 9 or 0. And then we do the same for a equals 2 and a equals 3. And there are no others. So summing these up, we get there are 11 lucky numbers. And verifying this with Python code, we find the same 11 numbers. So when a is 1, b is 1, and c is 4, for example, that gives 114. Question 29. A grid of squares measuring 9 units by 6 units has the 2 corners removed as shown. How many squares of any size are contained within this grid? So this is a bit easier if these 2 squares weren't removed. So what we're going to do is just add them back in and then subtract them. So when we add in the missing squares, then the number of 1 by 1 squares is 6 times 9, 2 by 2 is 5 times 8, 3 by 3 is 4 times 7, 4 by 4 is 3 times 6, 5 by 5 is 2 times 5, and 6 by 6 is 1 by 4. Adding all these up gives 154, but by removing each corner there are 6 less squares. So I'll just show that. We have 1, 2, 3, 4, 5, and 6 squares that are no longer possible without this square here. And the same for the other corner. So we have to subtract 12, giving a total of 142 squares. Question 30, the final question. On my calculator screen, the number 2659 can be read upside down as 6592. The digits that can be read upside down are 0125689 and are read as 0125986 respectively. Starting with 1, the 5th number that can be read upside down is 8, and the 15th is 21. What are the last 3 digits of the 2007th number that can be read upside down? So we can solve this by creating a pseudo base 7, where we use the upside down digits. So from 0, 1, 2, 3, 4, 5, 6, 7, sorry, just 6. 0 becomes 0, 1 becomes 1, 2 becomes 2, 3 becomes 5, 4 becomes 6, 5 becomes 8, and 6 becomes 9. Now we convert 2007 into regular base 7. So since it can be written as this is 7 squared and this is 7 cubed, it's 5565. And then in this pseudo base we've created, we just have to replace the 5 with an 8 and the 6 with a 9, giving 8898. And so the last 3 digits are 898. I also verified this with some Python code, which just creates a very long list of all the numbers that can be read upside down, and then prints the 2007 one in the list, and we get the same 8898, like so. So some cool questions in 2007. Thank you for watching.